In this video, what's going to be described is Ampere-Maxwell's law. And what this is this is really a correction to Ampere's law that Maxwell implemented and corrected. There's a mistake in Ampere's law. I wouldn't say it's necessarily a mistake. I would say it was more incomplete. So before we get to the correction, let's look at what the problem is. So if we look at a parallel plate capacitor, what we have is we have the current going down to plus Q, and then the current leaving minus Q. All right, so there's a potential here, but there's no mechanism, there's no material for the current to travel. So let's consider two surfaces. And so what we have is we have the first surface, which is blue, which is enclosed, all right? And we're going to represent that as L1. We then have the second surface, which is closed by surface number 1, and we're going to call that L2. Now, both of these surfaces are very valid in that they're both closed. And so what I want to do now is I'm going to apply Ampere's law to the first surface, and then I'm going to apply Ampere's law to the second surface. So if we apply Ampere's law to the first surface, L1, that's equal to mu naught I, because the current is clearly traveling through L1. It's clearly traveling through L1. Now, if I apply Ampere's law to the second surface, the current is not traveling through L2, all right? So our current is equal to 0. But that's a problem because we clearly see that the current is leaving the minus Q plate. So something's going on. Well, Maxwell solved this by adding a term to this portion of Ampere's law. And what he added was this ID. Now this mu naught is, once again, it's permittivity of free space. It's just going to be a constant, right? These constants are just to get, they're you know why the constants are added there. I'm not going to get into that. So what is this ID? Well, this is what's called the displacement current. And this is what Maxwell added to Ampere's law. So let's talk a little bit about what this displacement current really is. Now, what we can envision is that there are going to be electric field lines going from plus Q to minus Q. All right, so these are going to be electric field lines. Now, these electric field lines are passing through a surface, and so that should tell us right away, or should indicate to us, that what this really is this is an electric flux, that's going to be an electric flux. And so now, the displacement current is equal to the permittivity of free space times the change in the electric flux over time. Because what's going to happen over time is that this electric flux is going to change, right? There's going to be charge built up here. There's going to be a greater amount of potential. As that occurs, the flux is going to change over time. The flux through the surface is going to change over time. Now, when we see the flux, we see when we hear the flux, what we should think about is we should think about Gauss's law. And what Gauss's law is going to state is that the electric flux is equal to the sum of the electric field times the change in area, and that is equal to the charge inside. So it's going to be equal to this charge inside over the permittivity of free space. Now, we can plug this into our change in the electric flux. So now, if we plug that into our change for the electric flux, our ID is going to be equal to now the permittivity of free space. And what's going to change here is the charge is going to change. As the current is flowing through, the change in charge is going to occur there. So there will be a change in the charge over the change in time, and we still have this epsilon naught here. So with the epsilon naught here, we have the change in time, and the flux is going to change because the charge is going to change over time. This cancels, that's going to cancel, and what a change in charge over a change in time is it's really a current. It's really a current. And so now Ampere's law becomes, as I have written up there, B dot L is equal to mu naught I plus, now we have the mu naught from up here, and then our ID. Or we can say this is equal to mu naught I plus ID, or the displacement current. And what you want to think of the displacement current as is you want to think of it as the current that goes through surface 2 and into through surface 2 into this through the surface 2 and into the minus Q plate of our capacitor is how you want to think of that. And that's what Maxwell did in order to explain that phenomenon of the current traveling through there. If you have any questions, let me know.